This video will cover section 1.5, part 2, and this is more for my 7th period students because we didn't get to cover that, the whole section. However, if you are from my 2nd period class, we only had about 2 problems left, so you may fast forward the video until you get to the second to last slide or to the last part of the video. Okay, so we're going to talk about average rate of change of a function. And so what we're doing is comparing it to the slope because they are the same thing. But however, just in case you guys didn't know, you could take the slope or the rate of change of any function, not only linear functions such as this one. So yes, you could take the slope of a cubic function, you could take the slope of an exponential function, or any function in general. All you need is 2 points. And so from here, we're going to talk about something called the secant line. So just so you know, this line that you see here in red, that is the secant line. Okay, so I want you guys to write the following. Okay, so the average rate of change between any 2 points is the slope of the line containing the 2 points. So here we're saying average rate of change is the same as the slope, which is what I was mentioning to you guys. Now, that line, we're going to call it a secant line. And just so you know, whenever you take calculus, you will learn something about a tangent line. The difference between those two is that secant line calculates the average rate of change, and the tangent line will tell you the instantaneous rate of change. So that's just something good to know for the future. Let's go to the next slide. And again, here we have the average rate of change of a function. And just so we could refresh our minds, we are using the formula for y2 or y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. However, we know how to use function notation. So what we're going to do here is look at the formula in this way. And don't be intimidated by the function notation because you already know that f of x sub 2 is the same as y sub 2. And also f of x sub 1 is the same as y sub 1. So that is the same thing we're doing. And from the previous class, when we covered section 1.4, I did mention that the symbol is the one that looks like a triangle. It is the delta symbol. And that implies change. So this will be the change in y divided by the change in x. Okay, and here we have the graph of a polynomial. That's what it looks to me. It looks like. And so here we have the secant line. As you see, it touches the graph at 2 points, and it does cross the graph. A tangent line, the one that you will learn in calculus, it will only touch the graph at 1 point, and 1 point only. So we're not going to worry about that yet. Okay, so let's look at example 4, and we need to find the average rate of change of f of x, and we have this formula here, the equation of that function, which is a quadratic function. Also, we are given two x values. X sub 1 is equal to 0, and x sub 2 is equal to 1. So what we're going to do is find the y values, or the f of x sub 1 and the f of x sub 2. So for x sub 1 is equal to 0, we look at the function that we have here, and we could substitute it in there. So we will have f of x sub 1, which is f of 0. We substitute that 0 into the equation, and we will get 0 squared. Remember, this is the equation I'm looking at. So we will get the value of 0, because 0 squared is equal to 0. So from here, I have the point x sub 1 comma f of x sub 1 is equal to 0 comma 0. So let's just go ahead and plot that point here. And what I'm going to do next is find the next y value. So for x sub 2 equals to positive 1, we need to find f of x sub 2. And so that will be the f of 1. So we do have the equation is here, x squared, and that's what we need to do, substitute the x value into the equation. So 1 squared is equal to 1. So now from here, the point x sub 2 comma f of x sub 2 will become 1 comma 1. Here's my x value, x sub 2, and this is my function value. So let's go ahead and plot the point. And I would like for you to just trace the whole graph of the function, or to the best of your ability. So we know that 2 squared is equal to 4, and 3 squared is equal to 9. We know this function is even, so it is symmetric with respect to the y-axis. So I could just reflect every point across the y-axis. Or you could think of negative 1 squared is positive 1, negative 2 squared is positive 4, and negative 3 squared is positive 9. All right. Now let's go ahead and calculate the rate of change between those 2 points, and then we will trace the secant line. So the rate of change, by using the formula given to us, delta y over delta x, we know that we need f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. And so that will look like this. F of x sub 2 is 1 minus f of x sub 1, which is 0, over x sub 2 is equal to 1, and x sub 1 is equal to 0. So from here we get 1 over 1, which is 1. Now let's go ahead and trace that secant line that I was talking about, and we're going from this point to this point, and so we trace the line, and that is the secant line. Now we're going to do the same for the next problem. And again, we have x sub 1. Now here we have two distinct x values, different from part A. So let's go ahead and just trace the graph quickly. So we have 0, 0, 1, 1, 2, 4, and 3, 9. We also have negative 1, 1, negative 2, 4, and negative 3, 9. And remember, we need arrows because that extends indefinitely. It is a quadratic function. So for x sub 1 equal to 1, I'm going to use the graph as a reference now. So I know that f of x sub 1, if I look at the graph, it's here. So the y value for that point is also 1. Now for x sub 2 is equal to 2, Looking at the graph, we know that the y value for this particular point here, it is 4. So now we can go ahead and apply our formula. And that one says the change in y, delta y, divided by the change in x, delta x, it is the f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. And so we already have those numbers. F of x sub 2 is here, that is a 2. I'm sorry, I meant to say. Okay, so going back, the x value was a 2, the y value was a 4. So f of x sub 2, we're referring to this one, right? So that will be a 4 minus f of x sub 1, so that will be here. That is equal to 1. And now we need the x sub 2, which is here, 2. And we need a minus x sub 1, which is here, a 1. So now we simplify, so 4 minus 1 is equal to 3. 2 minus 1 is equal to 1. And so the rate of change for this one, it is 3. Our answer here was 1. Okay, so I would like to draw the secant line, and consider now we're using this point here, and also, no, I'm sorry, we're not using, we're using 1, 1, and 2, 4. So we're using the point 1, 1, and 2, 4. So I'm going to trace the secant line. And you guys could see, if we could compare both of them, one is steeper than the other, steeper or more inclined. So that is kind of makes sense, because for the first one, the slope was a 1, the rate of change was 1 over 1. And if we look at the other one, it's a 3. 3 is bigger than 1, so the rate of change was 3 over 1. Okay, so we're going to go to the next slide. And here we have a problem, a word problem, also about the average rate of change. And so we have, when a person receives a drug injected into a muscle, the concentration of the drug in the body measured in milligrams per 100 milliliters is a function of the time elapsed after the injection, measured in hours. And yes, this is a true graph. It is from the book. However, if you look at your ebook, you can see the source of that data. So it is a function, we know. It passes the vertical line test, and we have the independent variable, it is time in hours, and the dependent variable is the drug concentration. That will be our vertical axis. So we are asked to find the average rate of change in the drug's concentration between 3 and 7 hours. And so you can see our points are already here for us. And we are going to be finding not the equation of the secant line, but the rate of change of that one. So we use our formula, of course, delta y over delta x. And we will be using this, f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. So here what we have is f of x sub 2, we will be using this value, 0.02, minus f of x sub 1, which is here, 0.05, over x sub 2, so it's here, 7 hours, minus x sub 1, which is 3, for 3 hours. So what we will get from here is negative 0.03 divided by 4. Okay, I need that value. Okay, so negative 0.03 divided by 4 is equal to negative 0.0075. And the interpretation for this will be that the average rate of change is negative 0.005, which means that the drug's concentration is decreasing. We know that because we have a negative rate of change, and of course you guys know how to determine if the graph is increasing or decreasing, and you can see clearly so once again, you can see clearly that the graph is decreasing for this interval, which is probably 3 hours, all the way to 12. But remember, once you take certain medicine or drug, it will never leave your body. It will always be there. The amount will get smaller and smaller, but it will never be 0. It just happens that sometimes it's negligible to certain tests, but it will always be in your body. So going back to the problem, so between 3 and 7 hours, the amount of drug, the concentration in the blood will decrease by negative 0.005 or 0.005, I should say that instead, will decrease by 0.005 milliliters, milligrams per 100 milliliters in your blood. Okay, so moving to the next problem. The next problem, we have average velocity. So first I would like for you to write the following. So the average velocity of an object is its change in position divided by the change in time. Between the starting and the ending position. So please write that down. Now let's look at the definition from our textbook. And here we have average velocity of an object. Suppose that a function expresses an object's position s of t in terms of time. So now here we're calling time our independent variable. So no more x, time. Also, instead of using f of x, we're using s of t. So this is our dependent variable. And I know that you guys are very used to having x and y or x and f of x. So now just think about other variables. So instead of x, we are using t for time. And instead of f of x, we are using s of t. Now, the formula that we're using for average velocity is the same formula that we're using for rate of change, or the same formula that we use for slope. It's just written differently. So delta S is the change in position divided by delta T, which is the change in time. Okay, so let's look at example 6, finding average velocity. So the distance, which is S of t in feet, traveled by a ball rolling down a ramp is given by the function S of t is equal to 5t squared. When t is the time in seconds after the ball is released, find the ball's average velocity from 2 seconds to 3 seconds. Okay, so we do have two of our independent quantities here, and we also have the equation for it. So to find the position at 2 seconds, which is S of t sub 1, or in other words, S of 2. So to find that, we're going to substitute 2 into our equation, which is given here, and that will be 5 times 2 squared. Here we will have 5, 2 squared we know is a 4, so 5 times 4 is 20. So we're going to keep that value for later. So that will be the position at 2 seconds. Now let's find the position at t sub 2, which is 3 seconds. And again, we're going to be using the equation. We're going to substitute the 3 into the equation. And that same equation, 5t squared, the one here. So S of t sub 2, the position at t sub 2, or the same as S of 3, will be 5 times 3 squared. So this becomes 5, and 3 squared is equal to 9. And we know that 5 times 9 is 45. All right, so now to answer the question, we need to find the average velocity. So we will be using the formula. And the average velocity is given by the change in position divided by the change in time. So we will be using S of t sub 2 minus S of t sub 1 divided by t sub 2 minus t sub 1. So I'm going to make my substitutions here. And S of t sub 2 is here, 45. S of t sub 1 is here, 20. Divided by t sub 2 is equal to 3 minus t sub 1, which is equal to 2. Remember, this was 3 seconds, 2 seconds. And so now we calculate that. 45 minus 20 is 25, and 3 minus 2 is equal to 1. So here the average average velocity was 45, and the problem was in feet, so we will say 45 feet per second. Okay, so now let's move on to the last one. And if you would like to pause the video and try to figure it out on your own, you're free to do so. I think that will be a great idea. And then you can play the video again to check your answer. So here my t sub 1 is 2, but my t sub 2 has changed to 2.5 seconds. So if you guys notice, it is a little different. Here it was 3 seconds, and here is 2.5 seconds. So it's getting a little closer or a little sooner than 3 seconds. So let's start by doing the same thing. We have t sub 1 is equal to 2, and we already know what the position will be of that object at 2 seconds because we found it here. And so we know that s of t sub 1 or s of 2 is equal to 20. Okay, now we still need to find for t sub 2, which is 2.5 seconds. And so we use the formula s of t sub 2. We use the equation, the same equation that we have here, and that will be 5 times, let me go back so I don't get lost, and this will be the position at 2.5 seconds. Remember, we're substituting that for t sub 2, 2.5. So now we use the equation of was given to us, and we have 5 times 2.5 squared. And so this will be 5 times 2.5 squared. What is 2.5 squared? Okay, thank you. 6.25. And so 5 times 6.25 is equal to 31.25. So remember that those are the values we're going to be using. And of course, 2.5 and 2. Okay, so let's go ahead and calculate the average velocity. And again, we will use formula s of t sub 2 minus s of t sub 1 divided by t sub 2 minus t sub 1. Okay, and s of t sub 2 is here, 31.25 minus s of t sub 1, which we know is here, 20, divided by t sub 2, that was 2.5, minus t sub 1, which is 2. And so that will give us 11.25 minus 0.5. And if we divide that, we will get 22.5. And our units, since this part is given in feet and this part is given in seconds, then our units will be 22.5 feet per second. Okay, so that is the answer of the problem. Let's go to the next slide. And there is one more for you to try. If you would like to pause the video, and I will write down the answer so that you can try it on your own, and then check with mine. So I'm going to write it a little different this time. So delta S over delta T. If you want to do it this way to save some time, you are free to do so. So we already know we're finding S of T sub 2. So I know T sub 2 is that. So S of 2.01 minus S of T sub 1. We got T sub 1 is 2. Divided by T sub 2, which is 2.01 minus 2. And so in this case, we get, if we substitute those values straight in the formula, that will be take place of this part minus 5 times 2 squared. Down here we'll have 2.01 minus 2. And so this will be 20.00. I'm sorry, I missed a number. 20.2005 minus 20 over 0.01. And so in this case, we will get 0.2005 divided by 0.01, which is equal to 20.05. Let's not forget our units, feet per second. We're talking about average velocity. And so that is the end of the problems. Now, I would like to just make an observation here. You notice the first problem that we worked on, we went from 2 seconds to 3 seconds. So the time difference was 1 second. Part B, we went from 2 seconds to 2.5 seconds. So the time difference was half a second or 0.5 seconds. Now, if we look at part C, our time we went from 2 seconds to 2.01 seconds. And so for that one, the time difference was only 0.01 seconds. So if you notice, the intervals are getting smaller and smaller. And so in calculus, this procedure leads to the concept of instantaneous velocity, what I was mentioning earlier about the tangent line. So instantaneous velocity is something that you will learn in calculus. And just to finish the section, we have a little picture here, and that also compares the lines that you see in red. Those are secant lines, average velocity. In this case, we're talking about the average rate of change. Those are the red lines. So you pick 1 point and the second point. But however, when you take calculus, of course, you will learn how to find that one, a tangent line. And so that will be, of course, related to your instantaneous rate of change. Okay, so we're going to stop the video here. So this concludes section 1.5.